Hey guys, our next topic within quantum mechanics is kind of a hodgepodge of topics together. We're going to talk about the Compton effect, which also supports the particle nature of light, a deBroglie wavelength, and E equals mc squared and how that relates. So the Compton effect is basically an experiment that was done by Compton that supports particle nature of light. Okay, the idea that light comes in discrete packets of energy called photons, or waves called photons. And Compton directed a beam of X-rays at graphite. So he took X-rays, shot them at graphite, a big block of graphite. The scattered X-rays had a longer wavelength than the incident rays. This scattering basically is dependent upon the angle at which the material was bombarded. So this means that they had less energy since some of the energy was absorbed by the graphite. So basically these X-ray photons, these X-rays, exhibited particle-like properties because energy and momentum were conserved. Because basically when they looked at the energy at which it hit, energy that was absorbed, and energy that basically of the ray that came off, they saw that energy and momentum were conserved and that it behaved like a particle would behave if you shot a particle at a surface. So if light, so that's Compton effect. You just have to kind of know about it, okay? And the idea that it supports the particle nature of light, the theory that light is also a particle. So we know that light also behaves like a wave. So we have the Compton effect, we have the photoelectric effect, which tells us it behaves like a particle, but we know that it behaves like a wave as well because principally, the biggest reason is because you can see diffraction when you run interference patterns. When you run light through even a single slit, diffraction slit, you can see that it creates interference patterns on the wall or whatever surface. So the idea is if light has both this wave nature and particle nature, does matter in itself have both too? And the answer is yes. Okay, so this is pretty revolutionary. It's the idea that electrons, and really any matter, but we've been able to see it experimentally shown with electrons. Electrons exhibit a wave nature as well. So Louis deBroglie discovered this, and he discovered that the wavelength of said electrons, this is the deBroglie wavelength, is equal to Planck's constant divided by the momentum of that electron, okay, or the mass times the velocity of the electron. So how fast that electron's going times its mass, 9.11 times 10 to the minus 31st kilograms. I think I have that right, at the bottom. And that tells us the wavelength in meters of that electron. And it's always going to be a really, 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 really tiny number. Very, very, very small number. So to support this idea, so deBroglie had a theory. Davison and Germer said, hey, we're going to test that theory and run an experiment. And they actually confirmed his ideas. Okay, so this is really cool. Electrons were passed through diffraction grating. So here's a diffraction grating. Okay, lots of little slits. And they took electrons and they shot them through there. And if they were particles, guys, if you shot it through one slit, either it's going to hit the slit or it's not. Okay, if it was just a particle. But the cool thing is that it exhibited basically diffraction. Those are intensity bands. It kind of exhibited, like we talked about before, waves of interference. You could see areas of constructive interference, areas of destructive interference, which is pretty spectacular considering we thought these electrons are just these little particles. But they also exhibit wave-like properties. Okay, so. And you'll do some work with these equations a little bit later, some practice. So this is a really cool application. The electron microscope, or microscopes can only resolve details that are slightly smaller than the wavelength of radiation that you use to illuminate the object. So if you use visible light, 400 to 700 nanometer wavelength light to view something, you can't see things that are smaller than the wavelength at which you are viewing them. So you can't see anything smaller than, say, 400 nanometers. Electrons, however, have a very, very small wavelength, deBroglie wavelength, so you can view things that are a lot smaller, okay, which is really cool. All right, Heisenberg's uncertainty principle. You only kind of have to know just the general idea, what is Heisenberg's uncertainty principle. And I think a lot of people have some misconceptions about it, so we're going to try to tease those out. So Heisenberg's uncertainty principle is the idea that you cannot know an object's position and its momentum at the same time. Okay? And when I say cannot, it has nothing to do with, well, scientists haven't discovered a way to do that yet. No. It has nothing to do with that. It's the idea that you literally can't. Okay? It has nothing to do with technology. It has nothing to do with not being able to resolve it because we're not smart enough. You cannot know. And this is the reason why. The act of viewing ultimately changes the momentum. If I have something I'm viewing, like an electron, and it's going really fast, and it's moving around, and I want to see it, I want to view it. So it's supposed to be an eyeball. Okay? And I'm viewing it. In order to view something, doesn't basically energy have to be reflected off of that object and reflected to your eyeball? Okay? Well, that photon of light that reflects off that electron, doesn't it change that electron's momentum in order for you to see it? Okay? So, if I go to look at an electron, to see it, a photon of light has to be reflected off of it and sent back to the eye. This photon collides with this electron, changing its position. So the act of viewing it changes its position because in order to see it, photons have to be reflected off of that object into your eye, and the very act of seeing its position will change its momentum. Okay? Because that energy, that photon, here's our little photon, when it reflects off, basically you have now changed that electron's momentum. Okay? All right, equals mc squared, a very, very popular equation here, okay? It's the idea that you can basically matter, if you were able to convert matter into energy, this is basically your relationship, okay? Equals mc squared. So the amount of energy that a given amount of mass has, multiply that by the speed of light squared, and that tells you how much energy you have. Now, in practicality, like using it in real life, it's a little more complicated than that. Okay, basically, when two subatomic particles combine, okay, like when two protons combine, in that combination, a little bit of mass it takes energy basically to combine those protons. Okay, so if I have a proton, okay. And let's just say I add that to a neutron. I want to combine a proton and a neutron. I want to add those suckers together. Okay. A proton has a mass of 1.007276 atomic mass units. You'll sometimes see it just written as like U, okay, instead of AMU. A neutron has a mass of 1.008665 AMUs, and when you put those together, the mass here for hydrogen is 2.01355 AMUs. Okay, now, basically, before they're combined, they have a given mass, okay? After they combine, the total mass of this hydrogen atom is going to be very slightly, less than the mass of these together. So, the mass of the reactants added together does not equal the mass of the hydrogen, and that's because it takes energy, okay, to do that. So let me just read this. So, when two subatomic particles combine, the mass of them before they combine is more than after they combine. Mass is converted directly into energy when they combine. It takes energy to combine them. Okay? The missing mass is converted into energy to combine them. This little bit of mass is called the mass defect, or delta M. Okay? So equals mc squared should really be written like this. And this is the binding energy, the energy it takes to bind them together. This is the mass defect. This is the amount of mass. This is the amount of mass that was converted directly into energy in order to combine them. And this is the speed of light. Okay, this is in kilograms. This is in joules. This is in meters per second. Okay. So let's figure out what the mass defect is here. So basically, think of it like this. It's really just whatever this is added up together, you're just going to subtract from whatever your products are. Okay. So your mass defect is the mass of the products minus the total mass of the reactants. Okay? So in this case, it's going to be mass of the products, 2.01355, minus the total mass of the reactants here, which is 2.015941. So the total mass defect, the total mass that was converted into pure energy in order to bind these together, the amount of mass that contributed to the binding energy is going to be negative 0.00239 AMUs. Now, that negative sign just means that that mass was quote-unquote lost. It was converted into energy. Okay? It doesn't matter if you add the mass of the products and subtract the mass of the reactants or the opposite. Really, you're just finding this absolute value. Okay? So anytime you get a negative sign here, just knock it off. Okay? Just pretend like it doesn't exist, because you really just want this absolute value of mass right here. Okay? Let's convert that to kilograms. Your conversion factor, guys, for AMUs or U's to kilograms is on your constant sheet. Okay? And basically, it's for every 1 AMU is 1.66 times 10 to the minus 27th kilograms. And you get, let's see, oh, I haven't done this yet. I probably should have done that. It's going to be 0.00239 times 1.66 times 10 to the minus 27th. Whoops, I didn't do that right. That's great. 0.00239 times 1.66 times 10 to the minus 27th. Try that again. You get 3.97 times 10 to the minus 30th kilograms. Okay, so guys, that's the amount of mass that was directly converted into energy. So let's figure out how much energy that's equal to. So E equals mc squared, delta mc squared. Okay, so that amount of energy is equal to 3.97 times 10 to the minus 36 times 3 times 10 to the 8th meters per second, and then that whole thing is squared. And so the amount of the binding energy is equal to 3.57 times 10 to the minus 13 joules. Okay, so that's how much energy it takes to combine a proton and a neutron. Okay, that's how much energy it takes to do that. Okay, all right. So the reason this is important is this happens with fusion or fission, and the sun does this every day. Okay, that's how we get energy from the sun, is it takes its mass, it combines it to form helium, hydrogens into helium. The amount of energy that's released is the energy that we feel as warmth from the sun. So let's work through the example on the back. Okay, this is an old AP question. So considering the following nuclear fusion reaction that uses deuterium as fuel. Okay, so here we have deuterium, 3 of them. Okay, and basically, if you're using it as fuel, you're basically combining those together to form a helium, and then a hydrogen, and then a neutron. Okay, so it says determine the mass defect of a single reaction given the following information. So here we have, that's just the answer. So here we have, it gives us the mass, remember AMUs is the same as U's, gives us the mass of hydrogen, helium, deuterium, your helium, your hydrogen 1, and your neutron. Okay, so for part A, mass defect, guys, is your delta M. Remember, it's just your products added together minus your reactants added together. Okay, so in this equation, it told us how much mass each of them was. Okay, it told us that this was 2.0141. It told us this helium was 4.0026. It told us this hydrogen was 1.0078. And this neutron is 1.0087. Okay? Alright, so all we have to do is just do the mass of the products minus the mass of the reactants. 4.0026 plus 1.0078 plus 1.0087. So that's the products minus the reactants. Remember, we have 3 of those deuteriums. Okay, so that's going to be 2.0141. And we get a mass defect of 0.0232 U's. Let's convert that into kilograms. Once again, that conversion factor, guys, is on your constant sheet. For every 1 AMU atomic mass unit, it's going to be 1.66 times 10 to the minus 27th kilograms. And that's 3.8512 times 10 to the minus 29th kilograms. That's your mass defect. That's the amount of mass that's converted directly into energy during this reaction. Pretty straightforward. So for part B, determine the energy in joules released during a single fusion reaction. Determine the amount of energy released. All right, well, here we go. This is our energy here. Equals mc squared. So it's going to be equal to our mass defect. 3.8512 times 10 to the minus 29th times the speed of light squared. And so that's going to be 3.47 times 10 to the minus 12 joules. And you might think, man, that's not a lot of joules. But, guys, that's for a single fusion reaction. Imagine how many billions and billions and billions of those are happening, for example, inside the sun. Okay? All right, and then part C says the United States requires 10 to the 20th joules per year to meet its energy needs. How many deuterium atoms would be necessary to provide this magnitude of energy? So how many deuterium atoms? So this right here. How many deuterium atoms is necessary to provide that much energy? Okay, well, we've got 10 to the 20th joules of energy that the United States needs. Okay, so let's see how much energy per reaction is happening. Okay, well, we know that for every reaction, there's 3.47 times 10 to the minus 12th joules. Okay, and that's per how many deuteriums? Well, there are 3 deuteriums. Deuteriums. Okay, in this reaction, right? Let's look. There's 3 of them right there. It tells us there's 3. Okay, so per deuterium, okay, that's going to be basically how many deuteriums do we need in order to produce that much energy. It's going to be 8.65 times 10 to the 31st deuteriums.